Hello. Hey, everyone. Thank you very much for staying with us up until the very last session of the day. Highly appreciate it. So my name is Maxime Visonneau. I'm here today alongside Laurent Bernaille. We are both working for Datadog as part of the infrastructure engineering group. And if we're here with you today, it's to talk to you about our story on how we operate our infrastructure over not only one, but 3 cloud providers now, and how Kubernetes helped us in that journey. We'll be happy to take questions after the talk. I'm not sure we'll have enough time, but happy to take them offline. Otherwise, you can always find us on the Kubernetes Slack. And in case you do not know about Datadog, we are a software as a service observability platform that and we aim to help our customers obtain better visibility into their infrastructure and applications. And to give you a bit of a sense of scale of what we operate at, we have about 800 integration as of today, and we handle more than 10 trillion events on a daily basis. If we're here today, it's to talk about Kubernetes. So on that front, we have hundreds of clusters, tens of thousands of nodes, and hundreds of thousands of pods. And they are all living in the cloud among 3 providers, public cloud providers, namely Azure, AWS, and GCP. And if we did that, spoiler alert, it wasn't because it was fun, surprisingly, perhaps, but we had some reasons to do so. First, our customers were looking for us to be close to them. There is also this interesting philosophy that we have at Datadog that we call dogfooding, which is basically looking to experiment as much as we can in order to potentially provide solutions that are more pertinent for our customers. If it solves our problem, potentially it solves theirs. And of course, more locations to operate from, and also a good starting point to establish partnerships with those providers. And so to get started, I'll hand it over to Laurent, who will get you into where we started and where we are today.
So let's start with a bit of history. Until 2018, Datadog was running on a single region in the US, on AWS, what we could refer to as Classic, and everything was operated with virtual machines managed by Chef, and applications were deployed with Capistrano. In 2018, we decided to expand, and we created our first region outside of the US on GCP in Europe. And over the years, we added more and more regions. So we started diversification by adding edge data centers, from which we run synthetics and browser tests. We had our first certifications, and in 2021, we had a big expansion where we created 3 new regions, one for a government agency in the US. And we continued. Last year, 2 years ago, we opened our first region in Asia, in Tokyo. And we continue added edge regions, and this is where we stand today as of the first quarter of 2025. To summarize this in a few numbers, we currently operate over 3 different cloud providers. We have 6 main large regions, and we have 29 edge locations. To make that work, we had to find a solution, right? And of course, as Maxime was saying, one of the reasons we're sharing it here today is because we're using Kubernetes to make it work. And as a reminder, this is how we started at Datadog, right? Everything was running on AWS. It was simple enough. When we wanted to deploy applications, we were using a set of tools, Terraform, Chef, Capistrano, some Packer. That was easy. When we added our first region outside of AWS, we decided to pick GCP in Europe, and we had to decide what to do next, right? So were we going to rewrite everything we had written for AWS, or were we going to try and find something that was more cloud agnostic? And the big question is, can we have an infrastructure abstraction so we can consider different regions in the same way? And of course, I'm sure you know the answer. The answer felt very clear at the time. It was Kubernetes, right? And the idea is that Kubernetes offers us a unified way to interact with infra, right? You can software packaging in a unique way with containers. You have a unique way to define application rollout strategies and updates, and you have a way to define resources that will be cloud agnostic. And of course, this was working on all the providers we were considering at the time. So far, our applications were running in nodes, and what we wanted to move to is to move to applications running in containers in Kubernetes. And There are additional reasons, right, to move to Kubernetes. As I was saying, abstracting the infra was the first one and the most important one for us. But something that was important too, very similar to using multiple clouds, is that our customers were starting to run Kubernetes in 2018, and we were not. And so in order to make our integration and our support for Kubernetes better, it made a lot of sense for us to also run on Kubernetes. In addition, the community was pretty big at the time. It's even bigger now, which means like we have a lot of people to talk to when we have challenges or issues. And finally, and it's important too, right, it was much easier to hire people in the infra space when you're running on Kubernetes at the time. So now we have the answer. Let's go, right? However, now that we've said that we want to do Kubernetes, we need to figure out how we're going to do it. And I'm sure you remember Kubernetes the hard way from Kelsey Hightower, but it can be a bit overwhelming at the beginning, right? You have a lot of concepts you need to care about. In 2018, when we started, of course, we considered using managed Kubernetes, right? All cloud providers had offerings, so EKS, GKE, and AKS. However, remember, we were early 2018, right? And at that time, the landscape was pretty different. EKS and AKS were very young and still in beta. And while GKE was generally available, it was limited to 500 node cluster. And at the time, we already knew we needed much bigger clusters. In addition, managed Kubernetes clusters come with a lot of things that a cloud provider put in them, right? They're very opinionated. Because each cloud provider has its own way of implementing things. They're very similar, but they're different enough that it's a bit painful to build an abstraction on top of them. And we put a few examples there, like networking is different, operating systems are different, supported Kubernetes versions can be different. And something we also cared about, and we still care about, is this managed offering offered very limited observability on the control plane. And if you've run Kubernetes at scale, I'm sure you know that when you have an issue, you need to understand what's happening with API servers, etcd, which you can't see when you have a managed offering. So we decided to do it ourselves. Over the years, we went through multiple iterations. So we started pretty simple, right? We deployed the control plane of our cluster in virtual machines, and all the worker nodes were also virtual machines. You can recognize here the main components of the control plane. And we managed all this with Glue. I mean, we were familiar with Terraform, Ansible, and Packer, and of course, shell scripts, so we had a lot of those. And now that we had clusters, we could deploy applications. But remember, I mean, we were starting to have 2 regions at the time, and we knew we were soon going to have more than 2. And we need to provide a way for applications to deploy to all these regions. To make things even more complex, clusters have limit, right? I mentioned 500 nodes before. It turned out we're trying to limit our clusters to 5,000 nodes, but even with 5,000 nodes, in some regions, we need more than one. And if we want the schema to be the diagram to be more complete, regions actually each have multiple clusters. Which makes the life of application developers a bit tricky, right? Because they want to deploy their application in all the regions we support at Datadog, but it's starting to be difficult because they need to figure out which cluster they deploy to. They need to figure out if regions are slightly different from one another. And also in terms of workflow, right? If you do a deployment on a region and it breaks, maybe you want to stop and not continue to another region. So we had to find a way to make this easy for applications. And we actually implemented a solution that we call the software delivery platform. And here is a quick illustration of how it works, right? So when application developers want to deploy their application, what they do is they use the platform. And in this example here, we're going to update application A from version blue to version green. And what happens is, well, the application team is going to call the platform and update it to this version. And what's going to happen is, actually, this platform is going to start a temporal workflow where we encode all the logic to deploy. And to give you an example of a typical workflow, what's going to happen is we're going to start deploying to a first region here, Asia in the US. And then we're going to check that everything is working fine by looking at monitors and alerts with Datadog metrics. And if everything is OK, sometimes we also want to wait for some time to make sure that things are stable enough. If everything is fine, we proceed and we continue to the second region, right? So in that example here, we've now updated the application A on GCP, and finally we do the same thing where we verify everything, and if it's okay, we proceed with AWS, last check, and now we're happy, right? The application has been updated. So we now have a good story for applications, right? But for infrastructure components, we don't have a good story there, right? Because as I was saying, we're application team tend to care about a single cluster in each region, but as an infra team, we actually have to care about all the clusters, which means updates are pretty painful, right? Because imagine when you have dozens or hundreds of clusters. And so our operating model is slightly different from application team because in our case, we're using Terraform, we're using Ansible, and so updating a control plane means running Terraform container updates. And this is one of the big shifts we did a few years back, where we decided to run Kubernetes in a different way. So if you remember the way our cluster were looking like, right? Everything was running in VM and managed with, as I was saying, Terraform, Ansible, and Packer. And what we realized, and we're not the only ones to do this, right, is that instead of running application in this cluster, we could also actually run control plane components. If you can see here at the bottom of the slide, instead of having application A, application B, we now have pods running Kubernetes control plane components. And what's interesting there is now, if we want to update a control plane, we can actually use the same primitive we use to deploy application, which is we can just use Helm and just update and roll out our control plane. Of course, in this example, we have a single cluster, but you can actually have multiple ones, right? So just to summarize this slide, on the top, you have the control plane of a parent cluster, which we still have to manage with virtual machines because we have to start somewhere. And just lower, you have the worker node from this cluster, where we actually run the control planes of the child clusters, right? And all this is running as pods, and we can run the control plane for multiple clusters in the same parent. And finally, on the left-hand side of the slide, you have the actual worker nodes for all these clusters. And this is where we are today, and as you can see, we still have to manage some Terraform and some Ansible code, but in terms of orders of magnitude, we manage dozens of clusters with Kubernetes now, hundreds even, but only a few have to be managed with Terraform and Ansible. Still, we want to make this better, and one of the things we have in mind is maybe we can run the parent control plane in managed Kubernetes, in which case everything would be managed the same. We would just have to manage our cluster with Kubernetes. So if you remember, I said earlier that managed Kubernetes offerings were pretty different and hard to use. This is a bit of a specific case, right? Because it's only a single team that has to care about it, the team that is managing Kubernetes. And also, it's a very specific single use case, and so it's easier to adapt to the different needs. So it is much better to what we had before, right? So instead of running Terraform and Ansible, now what we can do is we can just have this ugly for loop here where we're just updating with Helm or our cluster. It's good, but it's not ideal. But if you remember, we actually have a tool that is allowing us to deploy application across multiple regions with logic to deploy it. It turned out if instead of deploying application, we try and deploy control plane components, what we can do here, and I'm going to take the example of etcd, is we can use exactly the same type of workflow to update control plane components. And here we're going to see how we update etcd from blue to green, and you're going to see that it's exactly what we were using before for applications, so we can leverage the tooling that we've built for other teams. And this is very similar, right? First, we're going to update in a region, then we're going to move to a second one. What's slightly different is we can iterate over multiple clusters in a region, and then the final region where we have 3 clusters. So let's recap, right? We now have a way to deploy our applications in multiple regions and cluster and different providers, and we have a good way to abstract our application using Kubernetes. However, one big question remains, which is, how good is this abstraction? And Maxime is going to talk about it.
Thank you. Thank you, Laurent. So yeah, so as you can see, as Laurent stated, we have now a way to help us unify how we run and deploy application across multiple cloud providers. But one question remains indeed, like how far does this abstraction actually goes and where does it start leaking? And so as under Kubernetes, we are still heavily relying on cloud-native primitives such as compute, storage, or network. This is where things start to get tricky when you look into making that work over multiple providers. Because while Kubernetes gives us a consistent API that all sales infrastructure group and application teams can leverage in order to interact with, the underlying infrastructure remains widely different from one provider to the other. So let's dig into each one of them a bit, and let's start with compute. So at the compute layer, there are two key resources that we care about, mainly pods and nodes. Pods are our new way to deploy our application, whilst the nodes represents the actual underlying compute resources on which pods are being scheduled on. Hopefully, I'm not learning you anything there. But if you recall beforehand, before we were using Kubernetes, every app we were operating had a native implementation over dedicated instances that were dynamically scaled through, well, in the case of AWS, auto-scaling groups. And as everyone in the engineering group at Datadog was very familiar with this approach, we decided to get the migration much easier on everyone's hands, to start with a very similar one by having a single pod per node. And the main advantage of that, well, of course, being able to migrate a bit more quickly, but also preventing ourselves with any kind of upcoming quirks that Kubernetes brings along the way, such as like having applications competing for the same resources over the same node, and potentially also keeping the capabilities that users were already used to, such as having local disks or any kind of accelerators that needs to be solely accessed by a single application. And here as well, similarly as before, our general idea was to continue relying on the same underlying primitives that, well, services that the providers was offering us, such as auto-scaling groups. But from a maintainability perspective, though, we had to find a way to efficiently manage all those scaling groups among those providers. And this is where Kubernetes can come quite handy, because if you are missing an abstraction, well, you can build it yourself, thanks to custom resource definitions. And this is what, by heavily inspiring ourselves from what the cloud providers do for their respective managed Kubernetes offerings, decided to do as well. So we introduced this concept of node groups that we therefore offered to our users. And that way they could have a way to declare the instances that they were expecting to have to run their workloads in a unified fashion. And the idea there was to really keep it simple for them. They declare what they need, and we take care of implementing it on our hand. So from there on, when users were looking to deploy their applications, they would start by defining node groups that represents what they need. And ourselves, we operate a controller on each cluster that can reconcile those configured node groups, basically making the necessary API calls to the underlying provider. In the case of AWS, for example, creating the associated auto-scaling groups. And finally, we decided to leverage the cluster autoscaler in order to determine how many nodes we need for within each of these groups, according to the amount of pods that the user was expecting to have to schedule. And the cool thing with that is that, well, the cluster autoscaler came up out of the box with support for all the providers we were aiming to operate on. And we had to make our controller do the same. But as long as we have that, we can technically support any kind of provider while having a unified abstraction for the users. And thanks to this approach, but most importantly, thanks to the huge effort from the entire engineering group at Datadog, at some point, we eventually managed to migrate the entireness of our applications over Kubernetes. And as you can imagine, though, this solution started to quickly show its limits. Of course, the abstraction was quite leaky, as users would still have to configure their instance types, figuring out on which cloud providers they reside on. And also in terms of efficiency, figuring out what instance types you need for your workload is a hard task to do. And if you, well, especially on three providers where you may not have the equivalence from one to another. And last but not least, in terms of scalability as well, it posed quite some challenges, as for any kind of pod that you need to schedule, you need a new node, so it adds up in terms of latency. And when you start managing hundreds or thousands of autoscaler within your AWS or GCP or Azure account, it starts to quickly put pressure over the API, the cloud provider APIs. And so for those who started with Kubernetes more recently, this might seem obvious. But of course, we want our users to focus on pods rather than nodes, right? So in order to move from where we started to a more future-proof approach, we had to start somewhere. And it began by ensuring that every pod every pod specs were embracing this habit of specifying resources requests and limits. And as you can see here as well, and here as well, I'm not learning you anything, but this is a much more abstracted way to represent what our application needs in terms of resources rather than specifying a particular instance type. And so once we had consistent pod specs being set among our apps, we were able to start flipping the model and start managing node groups on behalf of our users. So application teams that were ready to make the move, having updated their node spec, we could happily onboard them onto those set of managed node groups that infrastructure team would be looking after, whilst others who still needed to have like a strong ownership of the instance they are operating on and willing to maintain that themselves could remain with that approach. But aside from the maintainability win on both sides, what it brought us as well, the fact that we could manage those node groups as part of the infrastructure group, it allowed us to start introducing new instance categories, for instance, such as varying CPU architecture or instances with accelerators. And whilst nothing was technically preventing users of dedicated node groups from doing so, these options were being made accessible without any kind of effort on their end, which made the overall approach quite appealing for everyone. And on top of that, if we were to go even deeper than this, we could, example, start using different hardware generation that allows us to figure out what's the most cost-effective instance types given a particular need, right? And all of that without interfering with the application team's workflows. Which leads us to our third and last step in that process, which was we were now being able to focus onto how can we efficiently size our instance fleet. And I'm not going to risk myself at paraphrasing what our colleague Rahul and Ben did yesterday in this exact room, actually. So I hope that the recording will be available soon, but they dig into that particular topic in quite some depth. And of course, there is much more things to say about compute, but we also have stuff to say about the other things. So I'll continue with storage now. Similarly here, there is a few Kubernetes primitives that we can relate to. When we talk about storage as an abstraction in Kubernetes, what we are mainly referring to usually is how can we provide our pods with access to block devices. And when you operate in the cloud, there are two ways you can have those block devices. Either they are local to the instances that the pods are being scheduled on, or they are remotely managed by the cloud providers, and that way they can follow up the lifecycle of your application if the pod moves from one node to the other. Thankfully here, containers have been around for a while now, and the community has been looking into ways to standardize how can we approach this from an even broader perspective than Kubernetes, actually. And thanks to the container storage interface, now we can rely on providers to implement drivers that satisfies the spec of the standardization. And the great thing with that is that we get out-of-the-box support for all of the providers that, in our case, we were looking for. But as interestingly as well, we have more operational capabilities, such as, thanks to additional abstractions, we can potentially snapshot the volumes. On the other hand, what we've discovered along the way is that managing block devices among multiple cloud providers is quite challenging. It has a whole set of challenges. First of all, the offering is often quite inconsistent from one another, which means that it's very hard to offer a unified user experience among them all. On top of that, as I was saying, each provider is maintaining their own drivers, so maturity can largely differ from one another. So same here in terms of scalability, we do not necessarily have the same experience from one provider to the other. And last but not least, migrating or any kind of migration effort is often an afterthought whenever there is a new feature coming up or whenever there is an update that needs to go through. Quite often it involves a lot of manual effort to get it through. On top of that, if we jump back early 2018, CSI support in Kubernetes was not a thing yet. So that means that back then, Kubernetes was implementing those abstractions on its own way, which eventually led us to have to migrate towards the CSI way a bit later. And here as well, if you're interested into learning more about this, our colleagues Antoine and Baptiste did an amazing talk last year at KubeCon, where they talk about the intricacies of this migration. And finally, what about network? Here as well, multiple facets to comprehend, but most importantly, when we talk about networking in communities, at least at Datadog, what we were looking for was to have our pods being able to communicate with each other, whether they were being scheduled on the same cluster or among different clusters. And more generally, we were looking for our pods to have the possibility to access any kind of entities on our network. So at the time, it was very common to use overlay networks to do so, but ourselves at Datadog, we decided to not go towards that path, and we went straight away with addressing our pods natively over each cloud provider's respective software-defined networks. And the main reason behind this is that we were looking to avoid the performance overhead that we would have got by having our packets flowing through a tunnel. We also felt that in general it would be more reliable because there would be less moving pieces in our data path. And last but not least, as I mentioned before, we were looking to have connectivity between two pods from one cluster to another. And that's what we could get, as every single pod had an IP on the underlying network. They could have cross-network connectivity. On the challenging part, though, something that we've been facing from the beginning and that we've been continuously, getting ahead of myself. The main challenge when we implemented that part was that we had to deeply integrate with each of the cloud providers' SDN implementation. And back then, the ecosystem in 2018 in terms of network plugins was fairly limited compared to today. And so we had to use two different approaches and plugins depending on the provider we were running on. And this is why when we started looking into working onto Azure, we decided to shift towards a more unified approach, and we picked Cilium for that purpose. What it brought us here as well was the out-of-the-box support for all the providers we were looking for. More capabilities, such as network policy enforcement, better routing, thanks to the BPF perks and the replacement of kubeproxy, and also the possibility to collaborate with an amazing open source community. And this is what I was looking to get to before. The challenge back then, and that we are still looking into today mostly, is the scalability one. The scale at which we operate really leads us towards the intricacies of the solutions. So yeah, whether it's within a cluster or among clusters, that's what we aim to solve. And if you are here as well interested into the matter, we have made a talk with Amos and myself a couple of years ago at CiliumCon, where we dug into the matter. And with that, I'll leave it back to Laurent.
So Maxime told us about how we could abstract compute, storage, and networking, and the challenges associated with that. But of course, we also need higher level primitives, right? And cloud providers have a lot of high-level offerings, high-level services, and we have a few on these slides. However, because we wanted to run on multiple providers, we had additional constraints, right? We could only consider high-level services with common API across providers, Postgres being one, for instance. It had to support our scale, and also, last but not least, it had to be efficient in terms of cost because we run a pretty significant footprint. Based on these constraints, we picked a few services, right? We picked RDS for Postgres, Elasticache for Redis, and load balancers and object storage. However, and very similar to the other lower level offering, there are similar offerings between providers, but they are slightly different. Which means after a few years, our decisions have evolved on this topic. So the first one is, in terms of object storage, we use S3, GCS, and blob storage, and we're very happy with all of them, right? I mean, they are very similar interfaces and behaviors, and we're very happy with them, and we keep using them. In terms of load balancers, it would seem that load balancers are similar enough, but it turns out if you look at L7 load balancing, there are actually a lot of differences between providers, right? And that's why over the years, we've actually went down a layer, and we're now only considering layer 4 load balancing, and anything that has to do with L7 properties, we actually manage ourselves with Envoy. And finally, for database, and I'm saying Postgres and Redis here, we started with managed offering. We started with RDS and Cloud SQL, and it was working, right? But in the end, after some time, we had too many small issues where the behaviors of the different providers were different enough that it was starting to be painful, because while in theory, it was supposed to be similar between providers, and we would provide an abstraction to our users, all of them had to know the exact differences between all the providers and the constraints of all the providers. So because it became too painful, we actually implemented these services ourselves at a platform level. We learned a lot of lessons along the way, right? And one of the things we want to say is that the challenges we face, we talked a lot about the technical challenges, but the challenges are not only technical. The first thing is, well, if you want to run Kubernetes in multiple cloud providers at scale, you have to develop expertise. You have to understand exactly how Kubernetes works and these intricacies of the small issues you can get. But you also have to understand how the cloud providers work. In addition, you also very likely need to build strong relationship with providers, because, well, if you encounter a performance issue or an API issue, you need to be able to work with them. And of course, as you're offering a platform to the rest of your company, you need to be able to help them and train them to use the platform best. And finally, as always, when you're building a platform, we did a pretty good job at addressing 80% of the use cases, but we still have teams with very specific use cases where the platform we offer is not perfect yet, but we're working on it, and we're trying to iterate to support more and more use cases. And yes, I mean, Kubernetes offers a pretty compelling abstraction, but it has limits. It's a great way to describe application deployments, but it requires a lot of effort to make it work. And remember, I mean, if you run on a single cloud, but it's even more true on multiple cloud, is as soon as you start pushing the limits, the underlying implementation is going to leak, and you will have to understand it. Ideally, you would have only a few people that have to understand it, but you still have to understand it. And finally, something that's important too is, while managed services are getting more and more mature, what's happening is providers are trying to make their offering the best, and so a lot of the things that are happening there are not shared with the community, and it's happening internally, and it's much better, but it means that the behavior is becoming slightly more and more different between providers. In terms of perspective, there are a few things we're thinking about. We mentioned using managed Kubernetes clusters for control plane. We have a few other use cases that are where the use cases are specific enough and unique enough where it makes sense for us to make the effort to adapt applications to multiple managed offerings, so we're looking into that. We're also looking at new abstraction and capabilities. Maxime mentioned GPU earlier, of course, and GPU is a topic, and we have to support GPU for our users. And finally, I mean, we also have to improve our efficiency because we need to control our costs. Final thoughts, I mean, we talked a lot about how it was painful with Kubernetes, and it's certainly challenging, but without it, it would definitely have been much harder. And we learned a lot along the way. And on this slide, we want to thank you all, and of course we won't have time for questions because we're already a bit late, but we'll be around if you have questions, and you can reach us on Slack too. Thank you.